Okay, so now we write down what's left over. So 1 over r squared, partial r, k r squared. Okay, so let's do some simplifications. We know that k is a constant, right? So we can take it out of the derivative. Okay, so let's just erase it and take it out. On the contrary, you cannot take out r squared because r is the variable right now. So you cannot take out r squared. Okay, so keep that in mind. So let's moveegen to the other side. Okay, you moveegen to the other side, you get negativeegen. Okay, k over r squared, partial this, partial that. Okay, now you move this term to the other side. Okay, so if you do that, you get negative e gen. Okay, so the r squared will come to the top. So we have r squared, and then the k will go to the bottom. So divided by k, then we're left with the derivative term. Okay, so what you do now, okay, our objective here is to make t the subject, this t the subject. So we have to pick it out of the derivatives. So in order to remove the derivatives, we need to do the opposite of differentiation, which is integration. So differentiate with respect to r on both sides. So this derivative will cancel with this integral. Okay, this integral will cancel with this derivative. So you write down what's inside. And then okay, integration of r squared. So what you need to do is you apply the power rule. So power plus 1 divided by the new power. So the new power goes down here. And then now we move r to the other side, right? So, oh, sorry. Because you already performed an integration here, don't forget to add an arbitrary constant. Okay, don't forget. Every time you integrate, you must add the arbitrary constant. So divide both sides by r squared. Okay, so this cancels with this cancels with this. Yeah, and that's all. So you write that down. Okay, so now we again integrate to remove the derivative. So integrate with respect to r. So the integral will cancel with the derivative, leaving t. Then integration of r is simply uh you know let me write this down. So power plus 1, so r squared divided by the new power plus c1 over c1 over okay. Let's integrate this. So integral of 1 over r squared. Oh, let me check my solutions. Okay, yeah. Integral of r squared is the same as integral of r to the negative 2, which is power plus 1 divided by the new power. Then if you write this in positive index 1 will be 1 over r. Okay, so that means this shall become negative r and plus c2. Okay, so now we have our function t, right? This is actually t of r. So we do not know what C1 and C2 yet, right? So what you must do is you find it through the boundary conditions. Boundary conditions means what is happening physically at the boundaries. So the boundaries refer to the two extreme values of R that are possible in the sphere. What I mean is, okay, what's the smallest possible value of R in this sphere? It's R is equal to 0, right? Which refers to the center. That's the smallest extreme. Then what is the largest extreme? So what is the outer radius of the sphere? Which is 0.075. Okay, so let's consider the first boundary condition. Now, the first boundary condition is that I'm going to use is BC. Okay, sorry. The first boundary condition, okay, boundary condition 1, is the fact that at the center, the temperature is finite. Okay, the temperature at the center is finite, right? Temperature is a finite measure. Okay, a finite number. Temperature is a finite number. It cannot be infinite. It cannot be undefined. It cannot be negative. No, it can be negative if it's in degrees Celsius. Okay, so temperature is a finite value. And how are we going to use this to find C1 or C2? Okay, remember I've already went through this in the tutorials. So let's copy this temperature function and see what happens at the center. At the center, right, R is equal to 0, right? The value of R is equal to 0. So T of R equals 0 means wherever I see R, I replace it with 0, right? So if I replace this R with 0, okay, it doesn't matter, right? This is fine. So this whole term will be 0. What happens if I replace this R with 0? See, C1 over 0 is an undefined value. It's undefined. But this contradicts our boundary condition. See, temperature is finite, but the thing is, here, if we calculate when R equals 0, it will become undefined. Okay, so what is the value of C1 such that the middle term will not exist in the first place? Okay, what is the value of C1 such that the middle term will not exist in the first place? And that value is C1 is equal to 0, right? 0 is, it doesn't appear. Okay, 0 means it doesn't appear. So from this whole logic, we can conclude that C1 must be equal to 0. It must be equal to 0 so that the middle term does not appear. So that when the middle term disappears, right, we do not have the problem where R equals to 0, the whole expression will become undefined. Okay, so once we know that C1 is equal to 0, you go back and update your equation. You update your function. So we already know that this C1 is 0, right? So that means this entire middle term is 0. So what you do is you get rid of the middle term. So this you can make it into 0, and anywhere else, your dt dr expression, this can also become 0. Okay? Okay, so the next boundary condition I'm going to use is the heat transfer process at the surface. Wait, sorry, not the heat transfer process at the surface. I mean, the second boundary condition that I'm going to use is what's the physical condition happening at the surface, okay? When R is equal to 0.075. We already calculated the surface temperature, right? The surface temperature we calculated out to be 17.938. So the second boundary condition I'm going to use is when R is equal to 0.075, the temperature is 17.938 degrees Celsius. Okay. Do we know the temperature profile? Yes, we have the temperature profile, which refers to this expression. Okay, this expression is the temperature profile. We're going to substitute that. Okay, so negative E gen divided by 3K. Oh, sorry, divided by 6K. Sorry, yeah. 3K times R squared over 2 plus C2. Okay, this expression is evaluated when R is equal to 0.075. Right, I'm referring to this fact. Is equal to 17.938. Okay, so you substitute in the values. Okay, so C2 will be equal to 21.063. Yeah, so this is your value of C2. See, so you know your value of C1, you know your value of C2. So what you do is you substitute these values into here. So C1 already substituted. C2, we have yet to substitute it. Okay. Okay, so don't forget, our objective is to find this value, the center temperature of the sphere. Okay, the center temperature of the sphere. So we need to evaluate this, right? So what you do is you take the temperature function that you've already obtained. Okay, you take the temperature function that you already obtained. So the negative E gen over 3K multiplied by R squared over 0, right? But R is equal to 0 right now. So we substitute 0 squared over 2 plus C2. And what's the value of C2? This C2 is here. Okay, so this will be 21.063. 21.063. Then since this is 0, this whole thing is gone. Then what you're left with is 21.063 degrees Celsius. This is your center temperature of your sphere. Okay, so this is the first question.